Alright, so today I'm gonna be explaining another important article with the title Anonymous Walk Embeddings. This ICML paper in 2018. The task of representing entire graphs has seen a surge of prominent results, mainly due to learning convolutional neural networks and graph structured data, while CNNs demonstrate state-of-the-art performance in graph classification tasks. Such methods are supervised and therefore steer away from the original problem of network representation in task-agnostic manner. Here we coherently propose an approach for embedding entire graphs and show that our feature representations with SVM classifier increase classification accuracy of CNN algorithms and traditional graph kernels. For this, we describe a recently discovered graph object, anonymous walk, on which we design task-independent algorithms for learning graph representations in explicit and distributed way. So this is an example demonstrating the concept of anonymous walk. Two different random walks, random walk 1 and 2 of the graph correspond to the same anonymous walk. A random walk 3 corresponds to another anonymous walk 2. So this is how we create this. This is minimum of positions. This is the positional function, minimum of positions of each token from V sub I, from each node. And that is very important for structural representation. And you see a huge number of articles are working on this kind of representation, just for representation of structure. Both local structure, semi-global and global structure. They usually use it for local structure, not for global, because for global architecture, structure representation, we have a different, easier methods to compute, which is, for example, on the power of the adjacency matrix or random graph features and very interesting things that we can do. This is a feature-based model, AWE here. And they aggregate probabilities across all vertices in a graph and normalizing them by the total number of nodes. So when the length of anonymous walk grows, the number of anonymous walk grows as well. And the running time of anonymous walk embedding is of this order. So Dmax in or Dmax out is just the maximum for in or out degree in G. So as complete counting of all anonymous walks in a large graph may be infeasible, we describe a sampling approach to approximate the true distribution. In this fashion, we draw independently a set of m random walks and calculate its corresponding empirical distribution of anonymous walks. So for two discrete probability distributions, P and Q, we can define their L1. This is the L1 distance between two distributions. And our approach is analogous to the method of learning paragraph vectors in this paper, because there is an interesting analogy between sentences words in a sentence and the nodes in a graph. So you get the idea. So now you get the idea that you can use word2vec, any kind of representations that we used to do like this for word representations, word2vec algorithm. Very different methods had the problem with word2vec was, for example, we could overcome these problems of word2vec with either hierarchical sampling or negative sampling. So the same tools can be used here as well. And now we can use this representation for graph classification. Because we know the kernel function, we can measure the structural thing like this. For example, the kernel between two graphs can be obtained like this. Because you have representations of one graph and representation of another graph, so these two vectors, we can calculate the kernel of that, and this means that you have calculated, for example, the similarity between two graphs. Also, you can extend this idea for contrastive graph learning, which becomes much more interesting, but it's too much mathematical. It's not bio-inspired. And these are the data sets that we use for graph classification, like enzyme, DD, mutag. For example, mutag is for mutagen detection. And also they use it for social data sets as well. But biodata sets like mutag are used for, usually there are two classes. All of them are two classes. I remember this had 7 features, 2 classes, the rest of them 2 classes classification. Enzymes has always very low accuracy. Even today, it shouldn't be more than 50 or 60% because of the problems of this data set. And it's really hard. It's a hard data set.